The title is what? Exact solution?
To the pendulum.
Yep. Okay.
So, Ashtosh?
Yep.
Oh, it's me.
Oh,
yeah,
yeah.
Samuel's going to.
Yep. So we're doing the exact solution for a pendulum. So we're doing a derivative of the exact solution and also doing a derivation of the approximate solution for in terms of period time. And so we also did research onto a little bit onto the special function of the elliptical integral of the first order, which is used to solve the exact solution for a pendulum. And also we also show an implementation of a Python program which shows the difference between the exact and an approximate solution. Yep, just the difference. Next slide.
So I'm Ashutosh. So I'll be going through the derivation of the exact solution. And so here we have the differential equation modeling a free swinging pendulum, which is that equation that we had. So this is a second order nonlinear differential equation where theta is the angular displacement, t is the time, and g over L, where g represents the force of gravity, approximately pi squared or 9.81, and L represents the length of the string. So our main aim of our approach is to eventually integrate this with respect of time using our initial conditions, which I'll describe later, so that we can find the exact solution for the period. So what we're given is a second order nonlinear differential equation, and what we need to do is multiply by d theta over dt. So as we do that, this can further be represented as is represented in equation number 3, where we don't necessarily solve anything, but rather we rearrange the equation provided so that we get a first order nonlinear differential equation, like seen in equation number 3. Now, what we do is that now we have half d theta over dt squared minus g over L cos theta, which is equal to the constant. Why is it equal to the constant, you may ask? It's because when we look at equation number 3, when we differentiate the expression, we get 0. And you can only get 0 if you differentiate a constant. So therefore, equation 4 is equal to a constant. Now, if we further move forward, we've had half d theta over dt squared. So now we get rid of the half by multiplying by 2 on the left-hand side and multiplying 2 on the right-hand side. And that's how we end up getting equation number 5. And we get d theta over dt squared minus 2g over L cos theta equals 2c. Now 2c is still a constant, so we just name it capital C. Now, prior to continuing with the solution, we must consider that the oscillations of the pendulum are subjected to the initial conditions. So initial conditions, when when time is equal to 0, is theta subscript 0, which is our initial displacement. So initial displacement would be 4 theta subscript 0. Now we have d theta over dt when time is equal to 0 is also equal to 0. Now this is our initial angular velocity. So at the start, the angular velocity will be equal to 0. At the start, the initial displacement is equal to theta subscript 0. Now, when we go back to equation 5, we chose to replace 2g over L with the constant k and applied the initial conditions, which gave us equation number 6. And with equation number 6, we just found out that minus k cos theta subscript 0 is equal to constant c. And now we sub that back into equation number 5, which resulted in equation 7, which is the theta over dt squared, which is equal to k bracket cos theta minus cos theta subscript 0. Now here we have two cos thetas in this expression, right? So what we chose to do is we implemented the methods of double angle identities, which gave us so we used the method of double angle identities, which means that cos theta is equal to 1 minus 2 sine squared theta over 2. So now we sub this back into equation number 7, and now this gives us equation 9. which is d theta over dt squared equals k bracket minus 2 sine squared pi minus 2 sine squared theta over 2 plus 2 sine squared theta subscript 0 over 2. So now that we've done that, what we choose to do is we factor out the 2, and that gives us equation 10. So can you go on the next slide, please? Yeah. All right. So now that we had factored out the 2 from the previous step, we replaced the 2k in the front with another constant called r. We replaced it with another constant. Why? Because we just want to make our calculations simpler for our later steps. And letting k, and we also name one of our constants by saying k is equal to sine theta subscript 0 over 2. So this gives us a total equation of d theta over dt squared, which is equal to r bracket k squared minus sine squared theta over 2. Now that we have equation number 12, we have to simplify this down before we integrate this. So now we take the root of both sides, which gives us d theta over dt, which is equal to root r, and root r times root k squared minus sine squared theta over 2. Excuse me. And now what we do is that we divide both sides by root k squared minus sine squared theta over 2, which gives us equation number 14, as seen here. So this becomes our main equation that we have to integrate to find out what our exact solution for time is. So what we do now is that, remember the initial conditions we had, we integrate this with our initial conditions, which gives us equation 15, which is the integration with the upper bound being theta subscript 0 and the lower bound being 0, and that's the integration with respect to time of d theta over dt over root k squared minus sine squared theta over 2, which is equal to root r, and the integration with respect to time to find the angular displacement there. So the time it takes for the pendulum to swing from the initial displacement point theta subscript 0 to the origin point perpendicular to the ground 0 is equal to t on 4, a quarter of a period. And no, a full period is when the pendulum swings from the initial displacement to the final displacement on the opposite side and returns back to its initial point, t. So that's how we got t over 4. So t over 4 is basically what you get when you integrate with respect of time to find the angular displacement between those 2 points, between the theta subscript 0 and 0. And as you can see, I've described that in the notes above and also verbally. Now we basically have equation 16. So that's where you get t on 4, and this becomes our main equation that we have to integrate to find our exact solution. So what we do from here is that we look at the square root sign. We look at what we need to integrate, and we see that there is sine squared theta over 2. And what we've decided to do is that we name sine theta over 2 into k sine var theta. Now the reason why we've introduced var theta here is because we've been using theta all of this time, and now this is the first time that we are naming we're giving a variable the value of theta, and we don't want to confuse theta with something else. That's why we implement var theta to differentiate between the theta values and the other values. So note, by substituting this equation above back into equation number 16, we create the expression below, which is equation 17. Now equation 17 will be used later, but in the next step we will be doing implicit differentiation on sine theta over 2 is equal to k sine var theta. And here Samuel can take it.
But technically, can you do that?
Samuel?
Done?
Oh, sorry, I was
No,
muted.
Samuel's doing it.
Yep,
Awesome.
sorry, I was muted. So by implicit differentiation of the function above, we get half cos theta
No,
on
it's
2 d theta, which equals to k cos theta, k var,
What?
yeah, k cos var theta, d var theta. And then by using Pythagoras' theorem, where sine squared
midday.
theta plus cos squared theta equals to 1,
I think it's 12.
because we have a cos here, we can
3:30.
manipulate it
So I've got
to
Let me go after. I'm gonna get an
get
hour break.
square root 1
11 till
minus
12.
sine squared theta over 2 d theta. Which is this equation for cos theta over 2 d theta. Cos theta, yeah, d theta, which is also equal if in the previous solutions, sine squared theta over 2 d theta is equal to, well, we know that sine theta over 2 is d theta is equal to k sine var theta. So we substitute that, and then by continuing to simplify it, well, we can find the upper limits of the integral. Hold up. Yep. So for our equation up here for half cos theta onto differential,
Samael, no need to read the formulas. Just go ahead to the main point.
Yep.
Yeah.
So after doing this, we just simplify it. On the right side, we rearranged our information to get the period time, which will be equal to 4 square root g over L to k bracket k, which is the complete integral of the first kind, complete elliptic integral of the first kind. Yep, next page.
Okay, done.
Oh yeah, enough.
Okay, so now we have the approximate solution. The approximate solution is like where we take sine theta as theta for all small values of theta. But for this to work, theta must be in radians. So by using this, you can, and using harmonic oscillator, you can get that t is equal to 2 pi L, like square root of L on G.
Yep.
Okay.
So as before, we were talking about the derivation of an exact solution. We got our time period equals to 4 square root GL, and we had a special symbol, which was the complete integral of the first kind. Essentially, what the complete elliptic integral of the first kind is the arc length of an ellipse. And in this case, the elliptical order of the first kind is when the arc length is from pi on 2 to 0. As you can see in the formulas at the bottom, the first one is the elliptical integral, and the second one is the complete first elliptical integration of the first order. Mouthful.
Brana, sorry for my interrupting, because the time, okay, you went behind the time, even though Jason, okay, reminded us. You have been given only 10 minutes, but you explained too much, because from my evaluation, I see this is, okay, these are notes from some references, and you are reading these notes for us. Actually, you should do some work, and that you just present your work, the objective, and then the conclusion, okay, to be with the time and to see what you did by yourself, okay? Yeah. Did you get my point?
Yeah.
Because
So-
what you did, Samuel Ashtos and Pranav, okay, you explained as paper that is theoretical things. Okay, I don't think that you typed this one by yourself, but that's getting from other resources, which is actually not. This is the way of making the project. The project, it means you read papers and then you take the things that you need to put and to explain for us. And also here you have to talk your title about the exact solution, but you want to talk about approximate solution of the pendulum, and then you moved from theta to t straight away. However, you have to be consistent also with the theory, with the materials that you have to present us. Okay, I have to stop now
Yep.
because the time is enough. Okay, thank you very much for the
All right.
presentation. Okay, so only 3 people now, okay, in this project? Sorry, only 3 people, yeah?
Yep, just the 3 of us.
Okay, yes. Okay, thank you very much. Do you have other people? Sora?
I might just say thanks to Pranav and Samuel and Ashtush. It's what is being said here is very important. It was a good thing, and I'm glad that you did it. So thank you. Let me reassure you. Okay, let me reassure you that what you've done is valuable and valued. That's a very hard example. Actually, that turned up in one of the past papers for the first maths course years ago. So that was just quite a difficult thing. I don't think anybody got it out in that course. But what I wanted to say also was that you're getting a little bit of an insight into professional publication. You've got 3 staff members here with you, and the other staff members will tell you that when they publish, one of the things about publications as a mathematical scientist is concision. You have to be concise. And so this training here is not to make you feel bad today because you were drawn to a conclusion, but rather to encourage you and help you to understand that if you thought teaching was an easy thing, setting aside, it's not, is it? It's not easy to get the stuff across concisely and in a way that's easily digestible.